Welcome, ladies and gentlemen, to our last little mini review lecture. And today we're going to review a few concepts that we learned in this class by looking at the human body. So the first thing that I want to look at in the human body is the circulatory system. And the circulatory system operates on the principles of pressure and the flow of liquids. It uses your heart to pump blood around to your body, and blood brings oxygen and nutrients and things to all of the cells of your body. So if we look at the circulatory system, what we have is a set of pipes with a pump on it. So we have your heart here, and then we have basically a set of pipes through which a liquid flows. And blood is essentially water with some extra stuff in it. And we can see that when we look at the density. The density of blood is 1,060 kilograms per cubic meter. And the density of water, of course, is 1,000 kilograms per cubic meter. And remember, seawater was 1,030 kilograms per cubic meter. And we've all heard the statistics about how much of our body is made up of water. And indeed, your blood is essentially water with some extra stuff in it. Now, that extra stuff is all the most important stuff. It's the stuff that does all the work. But we can essentially think about it in terms of a liquid as water with some stuff in it. And it's water with even more stuff in it than seawater has in it. Okay? So the organ that drives the circulatory system is the heart, and the heart works by changing its volume. So imagine I have a heart here, and it can hold a certain amount of blood, and then when it squeezes in, it changes its volume, right? It becomes a different size. And when it does this, we know that liquids are effectively incompressible, right? They can be compressed a little bit, but not very much. They resist being compressed quite a bit. So essentially, when the heart changes its volume by this much, it has to move this volume of fluid out into the pipes, right? And then they go around, they go through all your body, right? Remember that our pressure equation, P equals P naught plus rho GH. And that was for something kind of like a fluid like this, right? Now, the pressure, remember if we change P naught is pushing down on the top here. If we change P naught, we change the pressure everywhere in the fluid at the same time, right? The same thing happens with the heart here. As it pushes liquid out this way, it changes the pressure everywhere in the body. It moves fluid all throughout the body, and it pushes blood into the other side of the heart, okay? So then, for the heart to pump more blood per unit time, the heart can either contract more, right? I've shown this little contraction, but it could potentially contract even more, right? And squeeze a bigger volume. Or, to pump more blood, it can contract faster. So if it contracted the same amount, but more times per minute, then it pumps more blood, right? And your heart actually regulates blood flow by adjusting both of these things. So for an average resting heartbeat, we might have something of a decrease in volume of, say, 70 milliliters. And then each time the heart beats, we're of course moving 70 milliliters of blood out one side of the heart and into the other side, right? So we move 70 milliliters of blood, say, into this artery or pipe, as we're thinking about it, and it goes out, it goes around the body, and then because it's pushing everywhere, the pressure increases everywhere, we push 70 milliliters of blood into the other side of the heart. And so then for an average heart rate, for a resting heart rate, we might have something like 72 beats per minute, okay? And so if we want to see how much blood the heart is moving per minute, we can just take the total volume to equal the change in volume of the heart times the rate, all right, or beats per minute. And for our case, we said for resting heart rate, it was 72 beats per minute, okay? And then this, what we'll get out is this VT, and it's a volume per unit time, right? So you can see our units here, our volume here, okay? So a milliliter is a unit of volume, right? And it's I believe it's a cubic centimeter. A liter is its own unit volume, but I think the conversion is 1 milliliter is 1 cubic centimeter. And then we have a rate, beats per minute. And so what we end up with is a volume per minute. Okay? And if we take this 70 milliliters and we take this 72 beats per minute, what we find is that this VT, this volume per minute for your heart, is about 5 liters per minute. Okay? And the human body generally has about 5 liters of blood. So this is cycling a volume equal to the full volume of blood in your body about every minute. Okay? But then during strenuous exercise, the heart might pump more like 30 to 35 liters a minute. Okay? Now, this is usually limited by the heart rate because the heart can only contract and fill so fast. So I know the general rule of thumb for your maximum heart rate is 220 minus your age. Okay? But let's take something a little lower and say that during some tough exercise, your heart is beating at 160 beats per minute. Okay? Then what must the contraction volume be? So let's say we're on the lower end of the range given before. So we're pumping a VT of 30 liters of blood per minute. Okay? Now with 160 beats per minute, then the contraction size, the change in volume of the heart, must be this VT over R, okay, which is equal to about 188 milliliters, okay? So each beat is then contracting the volume of the heart by more than twice the size of this resting heart rate, okay? So now let's look at a different effect in the circulatory system. You may know that if you're bleeding, you need to apply pressure to the wound to stop the blood flow, right? And this increased pressure just keeps the blood from getting out of the system at that point, right? You have some wound here, a break in the skin. You have a fluid in here, the blood. And you apply pressure here so that there's greater pressure outside than the pressure of the fluid here. And that holds it in, right? So you may have also heard that you should hold the wound up, if possible. And this is usually explained by saying that the pressure will be lower if the heart has to pump the blood uphill, right? And this makes some sense. But this gravitational interaction is also responsible for changes in blood pressure based on depth, right? So we can understand it through that lens as well. So remember, this was our equation from our fluids for pressure based on depth, okay? Where H is the depth below the surface, okay? So let's consider a cut on your hand. The hand is hanging at your side, and it's generally somewhere around half a body height below the point of lowest blood pressure in your body, okay, the top of your head. So we have our little person here, and his hands are, my person seems to be a chimpanzee or something, but his hands are about, say, halfway, okay? So one half, we'll use a capital H for height, I guess, right? Because we already have H in here, right? So let's use a different variable. We'll use capital H for height, okay? So let's say let's say that for me, that's generally, say, 87 centimeters below the top of my head. Okay, so H equals 0.87 meters. Okay? And then let's say that I get a cut on my hand and I apply pressure and I hold it up above my head as high as I can. Okay? So then let's say that, let's make this H1. Let's say that H2 is minus 0.44 meters. Okay? So let's say I can hold it 44 centimeters above my head. All right? So then what's the change in pressure from holding my hand up like this? So we can call the change in pressure P up minus P down, okay? And we'll call the pressure at the top of my head P naught. So P up minus P down, I'm going to erase this guy's legs here. P up minus P down. P up is going to be P naught, okay? And then in this case, the H is minus, right? This H2. So let's just leave this as a value, and we'll put the minus in here, okay? Because we're holding it above P naught, right? This is P naught. So rho G H2, okay? The minus being above, because in our equation, normally H is depth, the distance below, okay? And then P down is going to be, we're subtracting it, so minus P naught, okay? The pressure at the top of the head. And then plus, because this is our normal way of doing it, but we have the minus in front of here, so we get a minus on everything, right? Rho, where this is the density of blood, G, and then H1. And so then what I end up with, the P naughts cancel, right? And I end up with a minus rho G and then H1 plus H2, right? Both terms had a minus in front of them. And it's negative because the pressure is going down. When I put my hand above my head, the pressure goes down, right? So the change in pressure, this P up minus PD is a delta P, right? The change is going down, so I have a negative value. Now, alternatively, we could have said that in this picture, P naught was this point, right? Where my hand is above my head. And then what I would have for P, for delta P, is that P up would just be P naught, right? So delta P equals. P up would just be P naught. And then minus, and then it'd be P naught. And then remember, this is plus, so maybe I'll put parentheses around it and write it this way. P naught plus rho G. And then the distance that my hand is when it's down is H1 plus H2, right? And then that gives us the same answer, minus rho G, H1 plus H2, okay? And I point this out just to show, just to make it clear, this P naught could be anywhere, right? And it can be anywhere because this relationship is linear. So I can always pick any point to be P naught. And P naught is not 0. Okay, I want to make that really clear as we look at this. P naught is not 0. It's some pressure, okay? And it's some pressure that we're relating everything else to. But we could pick that reference pressure to be anywhere, right? So a natural point for the human body is the top of the head, but we could have picked it where the hand is held above as well, okay? And we get the same answer because the physics doesn't care how we do the math, right? The physics, as long as we describe the physical world correctly, will give us the right answer, okay? So we get this delta P equals minus rho G and then the sum of these heights, okay? And that gives us a pressure difference of about minus 13,608 pascals, okay? So then, let's say that this is a cut that you cover with your thumb, okay? And you're pressing with an area about the size of a nickel, okay? About the size of the nickel kind of US currency, right? The little coin. So a nickel Might be an area that you can press with the end of your thumb, okay? And a nickel has a radius of about 10.5 millimeters, okay? So it's 0.010605 meters, okay? So a radius of just barely over a centimeter, right? 10 millimeters is a centimeter. And so then that gives an area of this circle, right, is going to be pi r squared, okay? And then if we wanted to see how much kind of additional force, because I'm applying pressure to the wound with, say, with my thumb. It's a little cut on my hand, maybe. And I'm applying pressure with my thumb. The effect of holding my hand up is to lower the pressure on the inside, right? Which is, if we think about it, the same as increasing the pressure on the outside. Okay, so if I go back to my little picture here where I have the cut and then I have, my thumb pressing on it here, I have a pressure on the inside, P pressing out, and then I'm putting a pressure with my thumb, P pressing in, right? So, in effect, what I have is a difference of pressure right here where these two things meet, right? And lowering pressure on the inside is the same as increasing pressure on the outside. So if I think about being able to press on an area about the size of a nickel with my thumb, when I hold my hand up like that, how much additional pressure from my thumb would that be equivalent to? Okay? So I have this area, and then of course, the force is equal to the pressure times the area, right? And if I calculate that out, I end up with about 4.8 newtons, okay? And that's not a huge force, but it's not nothing either, right? And that's equal to the weight of something that has a mass of about a pound, okay? So it's like adding an extra pound on there, okay? And so that additional pressure is going to help you stop the bleeding of the wound, okay? That's why we hold the thing up high. And we can think about it as adding kind of a pound to the force that our thumb is pressing with, okay? Okay, so the last thing I want to look at with the circulatory system is closely related to the one that we just looked at, okay? The change in pressure as we held our hand above our head, okay? And that's the feeling that all of your blood is in your head when you're upside down, okay? So, of course, your body has evolved to be upright, right? And you developed to pretty much operate with this kind of, head far above your feet kind of setup, right? And so your circulatory system then has to have evolved to provide appropriate blood pressure to your head when you're standing up, right? Or when you're sitting upright. So when you lay down, the blood pressure is kind of the same everywhere in your body, right? You don't have much of a height here for the blood pressure to change. So it's kind of the same everywhere. When you're standing up, you have a lot more blood pressure in your feet than your head because you have this height, right? And again, P equals P naught plus rho GH, okay? But when we tip you upside down, right? If somebody holds you by your feet or something like that and holds you upside down, we immediately notice the change in blood pressure, right? Because we're used to a pressure when our head is up here, and now we have all this additional pressure in our head. We have the level of blood pressure that would normally be in your feet is now in your head, okay? And your feet, you don't notice because they've evolved from the beginning to be on the bottom, right? So they're used to this kind of pressure. This is the pressure that feels normal to them. But with your head, you're used to a lower pressure, okay? And you immediately feel the difference. And you notice that if we look at the change in pressure, it's just like the problem from the change in pressure in putting your hand up, okay? So normally you have P naught at the top of your head and your height above the ground, but now your feet are there. So P naught is the pressure in your feet, right? Or the pressure when your head is up on top. So delta P equals the pressure when your head is at the bottom is P naught plus rho GH, where H is your height, right? Minus the pressure when your head is at the top, which is just P naught, okay? And so we get that the change in pressure is rho GH, where H is your height and rho is the density of blood, okay? Now, the change in blood pressure when standing on your head then is going to be around 17,500 Pascal, okay? And you might not have a good idea about how much pressure 17,000 Pascal is, okay? We don't hear that. We don't hear things in Pascal a lot, so we don't have a good intuition for that. But a normal blood pressure might be around like 16,000 Pascal. So this is quite a change, right? It's a big change to go from 16,000 and then add 17,000, right? You're basically doubling the pressure in your head, right? And this makes it feel like all the blood is pooling in your head when you're upside down. And indeed, a little bit more blood will be in your head when you're upside down because the weight of all that blood is pressing it down in there and holding it down in there, okay? It doesn't circulate as quickly out as it would when your head was on top, okay? So the last thing that I want to look at in this lecture is torque and the musculoskeletal system, okay? Your skeletal muscles all move your body by applying torque across your joints, okay? In particular, muscles can only contract, okay? That's all they do. They're just made up of cells that can get shorter. So for something like your elbow, this means having a muscle on one side that bends the elbow this way, and then a muscle on the other side that bends the elbow back the other way, okay? Because each muscle can only pull. It can only get shorter, okay? That's where it applies force, is getting shorter. So for something like a bicep, if this is your arm and you're holding some weight out here in your hand, okay? For something like your bicep, this distance from the elbow kind of pivot point to where the bicep attaches, I think is usually around 4 centimeters. That was the best information I could find, okay? And then the physical size of the elbow causes these contracting muscles to always be pulling with at least a little moment arm, okay? So even when your arm is pretty much straight, the physical size of the elbow means that this muscle connects like this, and you get just a little tiny moment arm here, okay? Now your arm, that's where your bicep is the weakest. It's the hardest to bend your arm when it's straight because the moment arm is so small, okay? But then as it bends, the moment arm grows, okay? And the normal distance, we have this elbow at a 90-degree bend, all right? With the distance between these two is 4 centimeters, so our moment arm is 4 centimeters at this point, okay? So when we have this simple example here, where we have the forearm bones parallel to the ground, okay? And we say that the distance from the elbow pivot to the middle of the hand to here is 38 centimeters, okay? And then let's say that we have a center of mass of the arm at 16 centimeters out, okay? I think these should all be pretty realistic values, okay? And this is a little closer to the elbow because the forearm's a lot bigger around close to the elbow than it is out near the hand, right? And the hand doesn't really, it doesn't weigh that much, right? So the center of mass then is a little bit closer to the elbow because there's a little bit more mass as we get closer to the elbow, right? Especially for someone that say lifts weights regularly or something like that, they start to get a pretty beefy forearm, right? And that beef is all close to the elbow. And so let's say that the forearm and hand have a total mass, so we'll say M of the arm is 3.5 kilograms, Okay? And so we're gonna model that in this case as pulling down with MAG, with a force MAG at this center of mass of the arm. Okay? And then let's say this mass that's in our hand is 20 kilograms. Okay? That's about 44 pounds. So that's a pretty decent weight to be curling like this, right? So our person is pretty strong. They go to the gym, they work out. They're strong enough to curl 45 pounds in a hand. Okay? So the question is, how hard is the bicep muscle actually pulling? So when we look at this, if we use the kind of angular analog of Newton's second law, that's the torque one, right? The sum of the torques is equal to I alpha. Okay? And the sum of the torques is going to be each one of these things. Okay? So it's the force that the bicep applies upward. Okay? We'll make this our positive direction. Okay? Force that the bicep applies upward minus the mass of the arm times G minus the mass of the weight times G. Oh, my goodness. I've forgotten all the moment arm lengths. That's the whole point, right? We're doing torques. So let's call the distances A and then B and C. So this is FBA, right? Because the torque is R cross F and the R is A, and our forces are all, the reason I put the arm parallel to the ground is so that our angle in between is 90 degrees. Okay, so then this is equal to the magnitude of it, right? A cross product has a direction as well, but the magnitude is equal to RF sine theta, okay? And this, in this case, the theta is the angle between the two. So the angle between the force and the moment arm. And I've designed it such, I've written the problem so that we're at 90 degrees, so we just have RF for all of them, okay? So for the bicep, this is the force of the bicep times A. For the center of mass of the arm, this is M, A, G, and then B, right? And then for the mass of the weight way out here in the hand, it's M, G, big M, G, and then C. And then that's equal to, and then we'll say that the bicep is pulling just hard enough to lift the weight. Okay, so it's pulling hard enough to move it at a constant velocity. So it's not applying an acceleration anymore. It's moving it at a constant velocity. So we'll say the acceleration is 0. Okay? So then if we plug in numbers for this thing, you can see first off, let me make some space up here. You can see that FB then equals G times MA times B plus big M times C over A. Okay? So I move these two terms to the right side, right? And then I divide it by A. That's all we had to do. And then if we plug in numbers, we find that we get a force of 1999 newtons. Okay? Okay, so first off, this is to lift an object that has a mass of 20 kilograms. So what's the force, what's the weight of an object that has a mass of 20 kilograms on the surface of the Earth? So the weight of this object is going to be mg, right? And that's equal to 196 newtons, okay? So the force that the bicep is pulling with is like 10 times the force of just the weight of this object, right? And that's because, remember, when I had the picture here, the object is way out here. So it has this whole great big moment arm to pull down with. And the bicep has to pull up with just this little tiny moment arm here, A, right? We called that C. So if I'm pivoting around the joint right here, then to make this thing turn, I have to apply a much bigger force than this force, because the torque is dependent on both my distance from the axis of rotation and the force applied, right? So the weight in your hand kind of gets the advantage, the mechanical advantage here, of having this great big distance from the axis of rotation. The bicep, on the other hand, has this little tiny distance from the axis of rotation, so it has to pull really hard, okay? About, in this case, in our example here, about 10 times as hard as the weight of the object, okay? So now let's imagine instead that we have a calf, okay? And we're trying to stand on our tippy toes. So your leg comes down, and in your foot, you have a heel bone that sticks out a little bit, and your calf attaches to that, and that creates this little moment arm here, okay? We'll call that A in this case. And then when you stand on your tippy toes, the ball of your foot is out here somewhere, okay? We'll call that B. And so you stand up by pressing the ball of your foot into the ground, okay? And your foot's a lot shorter than your forearm, right? So B is more like 18 centimeters, okay? And this A from the heel bone, the best I could find for that is also about 4 centimeters, okay? Just like with the bicep. So let's say that your calf is going to pull up on your heel bone, right? And that's going to make you pivot around this axis right here. And it's going to make you pivot the foot pivot in this direction, right? We're going to pull up on it right here. And then the ground is going to push into the heel of your foot as hard as your foot pushes into the ground, right? That's Newton's third law. And it's going to push up with some force that's going to want to make it rotate this way, right? So we have these opposing forces trying to make the foot kind of rotate around the ankle, right? So then if we again apply the angular analog of Newton's second law, we would have the force of the calf times A minus the force of the ground, right, times B. And then again, we'll say that this is for a constant velocity, a constant angular velocity. Okay, so the angular acceleration is 0. So if we assume that the calf can pull up with the same force as the bicep that was in our example from before, then the force that the ground applies is the weight that we can lift, right? Because of Newton's third law. The ground pushes down as hard as we push down on the ground, or the ground pushes back up as hard as we push down on the ground, okay? So when we rotate the foot like this, we cause this, right? And we lift up like this. And this force pressed into the ground is the force that we press on the ground with. So this is going to tell us this force that the ground applies is what we can lift by applying this, okay? And we're finding what we can just barely lift, just with constant velocity, right? So if we do this, then Fg equals A over B Fc, right? And so if we say that the force that the calf can apply is the same as the force that the bicep applied in the first problem, then the amount that we could lift is 444 newtons, okay? And remember from the first problem, we were only lifting 196 newtons, right? A 20 kilogram object. So in this case, with the same applied force, we can lift much, much more weight. And in fact, this one would be a mass of around 45 kilograms, okay? So a little more than double. Now, with the calf, of course, we'd have to include your body in what it can lift. And indeed, the calf is a bigger muscle than the bicep. But even if it applied the same exact force, you'd be able to lift more weight in this calf raise than what the bicep curl was lifting, right? Even when we included the weight of the arm, we were only at 23.5 kilograms with the arm, right? Now with the calf and its setup, we're at 45 kilograms, even applying the same force by the muscle, okay? And so in general, when we go to the gym, we tend to think of the bicep as kind of a weak muscle. It usually can't lift very much. If you just sit really strictly, really still, and try to just bend your elbow up like that, it can't actually lift very much weight, especially compared to other muscles in your body. But this is due not only to the fact that the muscle isn't as big as some other muscles in your body, but also this mechanical advantage that's created by the way that your muscles attach in your body, okay? And the different lengths involved in the moment arms as you try to move things, okay? So the bicep doesn't feel as strong as other muscles because, one, it's not as big, and two, the bicep is at a really huge mechanical disadvantage, okay? One of the biggest mechanical disadvantages in the body, okay? It's connected to the elbow, really, really close to the elbow, and your arm is kind of long, okay? Now, this is really good for throwing things because if I move the inside of the elbow a little bit, the end of the arm is moving really fast, right? Because it has to move in an arc. So if I get this little picture out of the way, if I move this with some speed, this has to cover this big arc at the same time. So you can get your hand moving really fast without the inside of your elbow having to move that fast. So it's good for that, right? But it's not good for the strength of the joint, okay? For how much, say, weight or how much resistance it can work against when something is in your hand, okay? So there are advantages and disadvantages to different setups kind of these different joints. And the bicep in particular is really good for making the end of your arm move fast, your hand move fast, but not very good for making the end of your arm, your hand, being able to resist really large forces, okay? And when we go to the gym, when we go to lift weights and things like that, which we should all do for our health, we can use this to think about what we want to do based on our goals. And if you want to make a particular muscle bigger, you have to do movements where it can contract, okay? First and foremost, you have to remember that all it can do is get shorter. So you have to do movements where the muscle gets shorter if you want to make it work, okay? And if you want to make the muscle bigger while using smaller weights, then you have to put the muscle at a greater leverage disadvantage, right? A greater mechanical disadvantage. So a really good example of this is when I lifted weights a lot, I had a whole bunch of different things that I did, but I did a bunch of different things for chest. And one of them was a press, where if this is looking at the top of my head, I'm laying down on a bench and I press weights up like this, okay? And you can see that the weight is going to press down right here on my elbows, okay? So I have some distance, the length of my upper arm, B, and that distance is going to decide the torque that's on, as my shoulder rotates here, on the chest muscle. Okay? The chest muscle contracts and makes the arm go like this. Okay? But then another thing that you can do, a different exercise that you could do, was to hold your arms more straight out like this. Okay? Or maybe with just a little tiny bend in them. Okay? Like this. And then instead of pressing up, you kind of bear hug the weights up like this. Okay, you keep your arms in this shape and you kind of move the weights up in this arc like this, kind of bear hug them. And in that case, you can see you make the lever arm a lot longer, right? This A is much bigger than B as we pivot around the shoulder. And so we can use a lot less weight for this. And then in addition, because the elbow doesn't move, we don't use the tricep, the muscle on the back of the arm here, so we can use even less weight. And what this does is allow the chest to work without such big weights. In this motion, you can generally lift really big weights, okay? In this motion, you lift much smaller weights. But your chest, the muscle that's contracting, that's making your arms do this kind of bear hug motion, your chest is working oftentimes just as hard in this one. or at least nearly as hard. Okay? And you can do both of these different things to be able to work your chest with a wide range of weights and with different goals in mind. Okay? And so these kinds of things influence the different lifts that, say, like a bodybuilder might choose to do in the gym. And you see the bros at the gym doing all kinds of different stuff. And this is the kind of thing that dictates what those lifts actually accomplish, right? And, your average bro probably doesn't understand it in these terms, right? They don't understand that they're changing moment arms, and they're changing angles, and they're changing which muscles are able to contract to work on a lift. But they kind of apply this by feel, and they get a lot of experience with lifting weights, and they kind of do this by intuition without totally understanding how it works, right? And this kind of thing dictates, in a lot of ways, all the different modes of exercise that we've built up for different goals. Okay? So that concludes our lectures for the course. And we'll have one more bonus lecture just for fun, and then we'll take a nice, easy final, and we'll be done with the class for the semester.